Could we really deflect an asteroid heading for our Earth? In other words, save the Earth from asteroid impact? An expert explains NASA's latest DART mission. This is on The Conversation by Gail Ellis, Senior Lecturer, Physics, RMIT University. And I'm sorry, I have a cold. It's getting better. I'm sorry about my voice. Now, the NASA spacecraft the size of a golf cart has been directed to smash into an asteroid with the intention of knocking it slightly off course. The test aims to demonstrate our technology readiness, in this case, as what we have now, in case an actual asteroid threat is detected in the future. It's the Double Asteroid Redirect Test, or DART for short, lifted off aboard a SpaceX rocket from California November 23rd, and it will arrive at the target asteroid system September of next year. The mission will travel to the asteroid Didymos, meaning twins in Greek, and it's a member of an armor group of asteroids. Every 12 hours, Didymos is orbited by a mini-moon or moonlet Dimorphos. This smaller half of the pair, will be DART's target, the moonlet. We've all seen disaster movies in which an asteroid hits Earth. We also have scars on our Earth from asteroid and comet impacts, creating an extinction event similar to the one that killed off the dinosaurs 66 million years ago. Could it happen in the future? Will Earth actually has been bombarded frequently by small asteroids, ranging from 1 to 20 meters, that's 3 feet to 60 feet in diameter. Almost all asteroids of this size disintegrate in the atmosphere and are usually harmless. There is an inverse relationship between the size of these objects and the frequency of impact events. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. This is a map by NASA. It shows the impact events from 1994 to 2013. Small asteroids are the bolids that disintegrate in our Earth's atmosphere. The daytime is yellow and the nighttime is blue. Now, I may be wrong, but I think the blue is more. I don't know why. And you can also see the sizes there as well. So this is just basically a 9-year, a 20-year graph. Now, this means that here we get hit much more frequently by small objects than larger ones, simply because there are many more smaller objects in space. Asteroids with a 1 kilometer diameter strike Earth every 500,000 years on average. The most recent impact of this size is thought to have formed the Tanumir impact crater in Mauritania 20,000 years ago. Asteroids with an approximate 5 kilometer diameter impact Earth about every 20 million years, so that's huge. You can see the difference. The 2013 Chelyabinsk meteorite over Russia's Siberia damaged buildings in 6 Russian cities, injuring 1,500 people. That was estimated to be only 20 meters in diameter, about 60 feet. Now, assessing the risk, NASA's DART mission has been sparked by the threat and fear of a major asteroid hitting the Earth in the future, because as we know, the astronomers say it's not a matter of if, but of when. It will happen. Now, the Torino scale is a method for categorizing the impact hazard associated with near-Earth object, NEOs for short. It uses a scale from 0 to 10, where 0 means there is negligibly small chance of collision, and 10 means imminent collision, with the impacting object being large enough to precipitate a global disaster. The Chicxulub impact of Yucatan that put an end to the dinosaurs 66 million years ago was a Torino scale 10. The impacts that created the Barrier Crater and the 1908 Tunguska event both correspond to Torino scale 8. With the increase of online news and individuals' ability to film events, asteroid near misses tend to generate fear in the public. Currently, NASA is keeping a close eye on Asteroid Bennu, which is the object with the largest cumulative hazard rating right now. With a 500-meter diameter, that's about 1,500 feet, Bennu is capable of creating a 5-kilometer crater on Earth. That's about a 3-mile crater. However, NASA has also said there is a 99.943% chance the asteroid will miss us. They said we have to brace for impact. At one point in their orbit around the Sun, Didymos and Dimorphos, its little moon, come within about 5.9 million kilometers of Earth. This is still farther away than our moon, but it's very close in astronomical terms. So this is when DART will hit Dimorphos. DART will spend about 10 months traveling towards Didymos, and when it's close by, will change direction slightly to crash into Dimorphos at a speed of about 6.6 kilometers per second. The larger Didymos is 780 meters in diameter and thus makes a better target for DART to aim for. Once DART has detected the much smaller Dimorphos, just 160 meters in diameter, it can make a last-minute course correction to collide with the moonlet. The mass of Dimorphos is 4.8 million tons, and the mass of DART at impact will be about 550 kilometers. That's nothing compared, of course, to the moonlet. It will be traveling at 6.6 kilometers per second, and DART will be able to transfer a huge amount of momentum to Dimorphos to the point where it's expected to actually change the moonlet's orbit around Didymos. This change, to the tune of about 1%, will be detected by ground telescopes within weeks or months. While this may not seem like a lot, 1% is actually a promising shift. If DART were to slam into a lone asteroid, its orbital period around the Sun would change by only about 0.000006%, which would take many years to measure. So we'll be able to detect the 1% change from Earth, and meanwhile the pair will continue along its orbit around the Sun. DART will also deploy a small satellite 10 days before impact to capture everything. This is NASA's first mission dedicated to demonstrating a planetary defense technology technique at a cost of about $330 million. It's relatively cheap in space mission terms. The James Webb Telescope, set to launch next month, costs close to $10 billion. Now, there will be a little to no debris from DART impact. We can think of it in terms of comparable event on Earth. Imagine a train parked on the tracks but with no brakes. Another train comes along and collides with it. The train won't break apart or destroy one another, but will move off together. The stationary one will gain some speed, and the one impacted will also lose some speed. The trains continue to become a new system with different speeds than before. So we won't experience any impact, ripples, or debris from the DART mission. Is the effect really worth it? Results from the mission will tell us just how much mass and speed is needed to hit an asteroid that may pose a threat in the future. That's assuming it will be made up of the same material. Now, we already track the vast majority of asteroids that come close to our planet, so we would have early warning of any such object. That said, we have missed objects in the past. In October 2021, asteroid UA1 passed about 3,047 kilometers from Earth's surface, that's nothing, over Antarctica. We missed it because it approached from the direction of the Sun. At just 1 meter in size, it would not have caused much damage, but we should have seen it coming. Building a deflective system for a potential major asteroid threat would be difficult. We would have to act quickly and hit the target with very good aim. One candidate for such a system could be the new technology developed by the U.S. spaceflight company Spin Launch, which has designed technology to launch satellites into orbit at rapid speeds, and this device could also be used to fire masses at close passing asteroids. This is by The Conversation, by Gail Illis, Senior Lecturer of Physics, RMIT University. Please leave your comments and thank you for your support.